that you are solving for the intersection points of these two circles. And you imagine that these two circles are of the same radius for a start. So you can say that so that's circle 2 and that's circle 1.
Okay.
Making these two equal gives you that.
Mm-hmm.
Where they intersect, now you're looking for coordinates of the form x, y, where they intersect. So that's your coordinate, I suppose. Asterisk rather than plus. So obviously y, the y coordinate of circle 1 is equal to the y coordinate of circle 2. So if you're adding that y coordinate and it's the same as that one, you can get rid of the y's, and that means that the square of x coordinate here along the x-axis of 1 is equal to the square of this x coordinate minus a. And what you ultimately end up with is that this x coordinate where they intersect is a over 2, which is kind of intuitive if they are the same radius.
Mm-hmm.
So it's going to be halfway in between the centres. So then, using this, you feed that back into either one of those equations. So a over 2 squared plus y squared equals r squared. And you're trying to find the y coordinate where they intersect. And so rearranging, that would be a squared over 4 minus r squared equals minus y squared, which is not very useful, so just switch those around, make them all the negative of what they are. R squared minus a over 4 squared over 4 is y squared. So that's how you solve for the intersection points. You've got a measurement for A and you've got a measurement for the radius, and they're the only two measurements you need to find your y coordinates. Obviously you take the square root and you take the square root. So that works perfectly well as long as 2 radii is greater than the separation between the 2 centres of the circles. Where you start to have interesting solutions is where you have 2 circles which apparently are not connected. I don't know why I can't draw centres, but I can't. So that's A again, and that's R again, and that's R again. Clearly, A is greater than 2R. So if you say, you put some numbers in, so we'll let R equal 3 and A equal, call it 8 maybe. And so you've got a gap of 2 in between them. You feed that into that, and you end up with the square root of 9 minus 64 divided by 4, which would be 16, which is the square root of minus 5, sorry. And what's the square root of a negative number? That's your question. And they figured out, people who studied this, that there was only one way you could solve this, and that was to decide what the square root of negative 1 would be, which they termed I, and then take the square root of 5. So your calculator will throw an error if you try and take the negative square root.
Mm-hmm.
This is the imaginary unit quantity. And so that confuses people because automatically you say imaginary and they think, oh, it's okay, it's all in my head. They use a different definition of imaginary, like the literary definition, the dictionary definition, rather than the mathematical definition. So the mathematical definition of an imaginary number is it's a square root of a negative. So you can plot a third axis if you want. You say that this is x, it's here, this is y, and this is I. And so you find that these 2 points here are where these 2 circles actually intersect.
Okay.
So if you rotate that around the x-axis and make a solid of revolution for each one of the spheres, you end up with this big kind of circular locus where they interact. And then because you've defined I as being a z-axis as well, you've got 2 imaginary axes. So this circle exists in dimensions which you can't plot really on the x, y and z manifold x, y, z 3 axes. So what you've done is you've defined a completely new type of space which exists. So these 2 things apparently are they're independent, they're not connected. But mathematically speaking, they are connected, just in dimensions we don't perceive ordinarily and we can't plot on the ordinary axes.
Fascinating.
And so you've got the phenomenon of quantum entanglement, as an idea I like to play with, where you have a particle will emit 2 photons, for example, that go in opposite directions, and you can measure the spin on one particle, and the system has to be of a total spin equal to its initial state. So if you measure the spin on one photon as being +1, the spin on the other photon has to be -1. There's nothing else it can be. So if you have something like a neutron, which splits into a proton, an electron, and a tiny little particle called a neutrino, your neutron's got spin +½ say. Your proton at the end of it has spin +½. That means you have to have created one particle with spin +½ and one particle with spin -½. And you can detect these 2 particles. And you can manipulate these 2 particles. So you capture the electron, we'll say that has the spin -½ and you flip it over, you force it to have spin +½ instead. Doesn't matter how far away this neutrino is, they can have diverged to the point where they're on opposite sides of the universe at this point. This neutrino will flip over because it's still connected to this electron, and thus the total system has to have a total spin of +½ So Einstein hated this idea. He called it spooky action at a distance and wasn't convinced, but experiments have borne this out. It's called quantum entanglement. And it makes a lot more sense if everything is already interconnected. So if you flip this round, it's like a gear, then this is going to flip round as well. You know that the teeth intermesh, and so they're obviously they're mechanically connected. Whereas in this, they're not physically mechanically connected, but they are still mathematically connected, which is to say perhaps they are physically connected just through dimensions we don't perceive. So you have this whole idea that you've got imaginary dimensions which exist, they're hidden dimensions, and you can play endlessly with that idea. You have William Rowan Hamilton was an Irishman, and thus it's arguable that when he came up with this particular idea he was slightly drunk. But you don't have to have just one imaginary dimension. You can have 3. So this is, and everyone meets these in undergraduate math. You have I, you have J, and you have K. And so these are all imaginary quantities. So I squared is -1, J squared is -1, and K squared is -1. So any length in imaginary meters, an area which is bounded in imaginary space will be negative because it's an imaginary length multiplied by another imaginary length. You would think, however, Hamilton proposed that this was the case. So that's confusing. The area in this plane, so we'll say that's 5i maybe, and that's 6j. So 5i times 6j it turns out is 30k. So if you have an area with these two imaginary axes defining the sides, the area itself is also imaginary. So from this ij equals k, and you can carry on with that. So ij equals k, jk equals I, and then ki equals j. If you have a gyroscope, you've probably seen a demonstration. You've got the wheel that's attached to a shaft and a bit of string.
Mm-hmm.
And if the wheel's not moving, you hold the end of the shaft and you hold the string, and it will just fall, which makes perfect sense. Gravity applies to it. You spin the wheel, it will fall. It will just fall sideways, which is completely counterintuitive. And so, as well, if you have an electric field and a magnetic field, and you put an electron in that field, the electron will go at right angles to both of these two fields that you've imposed on it. So you can say that the electric field is I, the magnetic field is J, and the momentum, perhaps the mass of the electron or something, some quantity in the momentum of the electron is K, because Ij equals K. The electric field times magnetic field is direction of motion.
Mm-hmm.
So we use these all the time in physics, and because we learn them at high school and we never do the solution of quadratics that apparently don't have solutions, we never explore properly the fact that the square root of -1 is I. This whole realm of dimensionality is not a thing in our minds. It's not something we conceive of. It's just, this is all we learn to use math as a handy thing, and we learn not to apply it to the real world in quite so literal a fashion, I suppose. So this idea that you've got imaginary dimensions is an important one. Now, if you have car suspension, where you've got a damper and a spring and wheel and a car, spring constant, different K, damper constant, you end up with a characteristic equation for this. So if you call that displacement, we'll call it Z, because it's height. You have, the equation is of the form mass times the acceleration due to gravity, like the downwards force on the whole thing, has to be balanced by an upward acceleration and a resistance in the spring and a resistance in the damper. So you've got these three upward forces being balanced by this one big downward force. I suppose, just for clarity, put them in different colours. So that's the same mass being pulled downwards by gravity. So that mass times the gravitational field strength is equal to the mass times the acceleration. That's another way of writing, so like Z dot is Z over T, so Z double dot is Z over T squared.
Mm-hmm.
So this force, being pulled downwards, is equal to, when this goes over a bump, mz double dot plus cz dot, because the harder you push on a damper, the more resistance you get. The quicker you push it down, the harder it gets to push. And a spring, that's proportional to how much you compress the spring.
Mm.
So you've got this thing. Another way of writing z dot is